Geology, the forces shaping the world beneath your feet. Take a moment and look around you. The ground you're standing on, the mountains in the distance, the soil in which gardens grow. All of this exists because of forces so ancient and so powerful that they've been shaping our planet for billions of years. This is the realm of geology, a science that invites us to understand not just where we are, but how we came to be here at all. Geology is the science that studies Earth's materials, its structure, and its immense history. It focuses on the physical features of our planet, the rocks that compose it, and the processes that slowly, inexorably shape the world over time. From the ground beneath our feet to towering mountains that pierce the clouds, from quiet valleys to distant volcanoes that remind us of Earth's inner fire, geology explains how the planet we live on came to be. Before we journey deeper, let's pause to consider the word itself, geology. It comes to us from two ancient Greek words. Geo means earth, our home world. Logos means study or knowledge or discourse. Together, they form geology, the study of the earth. The ancient Greeks, those curious observers of nature, gave us this word, though the formal science of geology as we know it today emerged much later in the 18th and 19th centuries. But the root meaning remains simple and profound. Geology is earth knowledge. It's humanity's quest to understand the very ground of our existence. Now, let's begin that quest by looking inward, beneath the surface, to where the story truly starts. Deep below us, far beyond the reach of any drill or mine, Earth is not the solid, unchanging sphere it might appear to be. Our planet is made up of four main internal layers, each with its own character and role in the grand design. The outermost layer is the crust, that thin, solid shell where all life exists. It's so thin, in fact, that if Earth were the size of an apple, the crust would be no thicker than the apple skin. And yet, this fragile layer is our entire world. Beneath the crust lies the mantle, a vast region of hot, slowly flowing rock. The mantle makes up the majority of Earth's volume, and though it's solid, it behaves almost like a thick, sluggish liquid over geological time. This slow, churning motion in the mantle is what drives so much of what happens at the surface. It's the engine of Earth's restless nature. Deeper still, we reach Earth's outer core, a realm of liquid metal, mostly iron and nickel, heated to temperatures that rival the surface of the sun. And at the very center lies the inner core, solid despite the intense heat, held in that state by the crushing pressure of all the layers above it. Movement within these metallic depths generates something invisible but vital, Earth's magnetic field. This protective shield deflects harmful solar radiation and cosmic particles, making life on the surface possible. Without it, Earth's atmosphere might have been stripped away long ago, leaving behind a barren, lifeless rock. So even when the world around us appears still, the planet is alive with motion. Heat from the core drives convection in the mantle. That motion, in turn, creates forces that shape the surface in ways both subtle and spectacular. Earth's outer shell is not one continuous piece. It's broken into large tectonic plates, great fragments of crust, and upper mantle that float atop the softer, more pliable rock below. These plates move very slowly, only a few centimeters per year. You might think such a pace would be insignificant, but over millions of years, those centimeters add up. Continents drift, oceans open and close. Mountain ranges rise where none existed before. Where plates move apart, molten rock wells up from below, creating mid-ocean ridges. These underwater mountain ranges mark the birthplaces of new crust, fresh rock forming as the old moves away. Where plates collide, the results are even more dramatic. One plate may slide beneath another in a process called subduction, creating deep ocean trenches and chains of explosive volcanoes. Or two continental plates may crash together, crumpling and thrusting upward to form towering mountain ranges like the Himalayas, monuments to the immense power of colliding landmasses. And where plates slide past each other, grinding along their edges, faults form. These are fracture zones where stress builds slowly over decades or centuries, then releases suddenly in earthquakes. In these moments, the ground shakes, cities tremble, and we're reminded that the planet beneath us is not a passive stage, but an active participant in the story of life on Earth. These movements, these collisions and separations, create trenches, volcanoes, earthquakes, and many of the planet's most striking landscapes. The geography we take for granted is not fixed. It's the product of forces that never stop working, never rest, never cease their slow but relentless transformation of the world. Now let's zoom in a bit, shifting our focus from grand planetary movements to the very building blocks of the Earth itself. What is the crust made of? What are mountains, cliffs, and riverbeds composed of at their core? Rocks, solid mixtures of one or more minerals, each type telling a story of how it came to be. Geologists classify rocks into three main types, and each forms through a different process. Igneous rocks are born from fire. They form when magma or lava, molten rock from deep within the earth, cools and solidifies. If the cooling happens underground, slowly, the result is a coarse-grained rock like granite. If it happens quickly at the surface, the result is a fine-grained rock like basalt. Either way, igneous rocks are the original building blocks, the raw material from which much of the crust is made. Sedimentary rocks tell a different story, one of patience and accumulation. They form from layers of sediment, tiny particles of rock, mineral, or organic material that settle out of water or air. Over time, these layers are buried, compacted by the weight of new sediment above, and cemented together by minerals dissolved in groundwater. The result is rock formed in horizontal layers, like pages in a book. Sandstone, limestone, shale, each one preserves a moment in Earth's history, a snapshot of ancient seas, rivers, or deserts. Metamorphic rocks are rocks transformed. They begin as igneous, sedimentary, or even other metamorphic rocks, but then they're subjected to intense heat and pressure deep within the Earth. Under these extreme conditions, their mineral structure changes. Limestone becomes marble. Shale becomes slate. The rock doesn't melt, but it's remade, recrystallized into something new. These three rock types aren't isolated. They're linked through the rock cycle, a continuous, elegant process where rocks are created, transformed, broken down, and recycled over vast spans of time. Igneous rock weathers into sediment. Sediment becomes sedimentary rock. Heat and pressure transform it into metamorphic rock. Melting returns it to magma, which cools into igneous rock once more. The cycle continues endlessly, driven by Earth's internal heat and the erosive power of wind, water, and ice. This brings us to one of geology's most profound insights, the concept of deep time. We humans experience time in days, years, perhaps decades if we're fortunate. But Earth operates on a timescale so vast, it's almost impossible to comprehend. Geologists reconstruct this history by studying rock layers and the fossils they contain. The law of superposition, one of geology's foundational principles, tells us that in an undisturbed sequence of rocks, the lower layers are generally older than those above them. It seems simple, but it's a powerful tool. By examining the order of layers, scientists can piece together the sequence of events that shaped a landscape. Fossils add another dimension to this story. The remains or traces of ancient life appear in a predictable order through the rock layers. Certain fossils are found only in rocks of a certain age. By identifying these fossils, geologists can determine the relative ages of rocks from different locations, correlating events across continents and oceans. This work reveals a planet billions of years old, constantly changing long before humans appeared. 4.5 billion years. That's the approximate age of Earth. In the earliest days, our planet was a molten ball bombarded by asteroids, inhospitable to life. Over hundreds of millions of years, it cooled. A crust formed, oceans condensed from steam. And in those ancient seas, the first simple life emerged, invisible to the naked eye, but profound in its implications. Life left its mark in the rocks. Stromatolites, layered structures created by ancient microbes, are some of the oldest evidence of life on Earth. Later, more complex organisms appeared. Trilobites crawled across ancient seafloors. Great forests of ferns and early trees spread across the land. Their remains eventually compressed into coal. Dinosaurs rose and fell. Ice ages came and went, grinding continents beneath massive glaciers, then retreating, leaving behind valleys and lakes. Through it all, the rock record tells the story. Each layer, each fossil, each grain of sand is a word in Earth's autobiography. And we, living in the present, are reading it, interpreting it, learning what came before and how it shaped the world we inherited. But geology isn't just about the past. It's deeply relevant to our present and our future. Geological knowledge helps locate natural resources. The metals in our phones, the oil that powers our cars, the groundwater that sustains agriculture. All of these depend on geological processes that concentrated these materials in specific places over millions of years. Understanding how and where these resources form allows us to find them, extract them, and hopefully use them wisely. Geology also allows scientists to assess hazards. Earthquakes, volcanic eruptions, landslides, tsunamis. These events are not random acts of nature. They're the result of geological processes we can study and, to some extent, predict. By mapping fault lines, monitoring volcanic activity, and understanding the forces at work, geologists help communities prepare for disasters, saving countless lives. And perhaps most urgently today, geology helps us understand past climates and prepare for future environmental change. The rock record preserves evidence of ancient climates, ice ages, periods of warming, changes in sea level, the composition of ancient atmospheres. By studying these patterns, scientists can better understand how Earth's climate system works and how it might respond to changes happening now. In a time when humanity's impact on the planet is undeniable, geology gives us perspective. It reminds us that Earth is dynamic, resilient, but also sensitive to change. It shows us that small shifts, sustained over time, can have profound consequences. And it equips us with the knowledge to make informed decisions about how we live on, use, and protect this planet we call home. So when you step outside, take a moment to look down. The ground beneath your feet is not just dirt or rock. It's the product of unimaginable time, of forces that shaped continents and formed oceans. It's a record of life and extinction, of fire and ice, of motion that never ceases. Geology is the key to reading that record, to understanding the hidden forces shaping the world beneath your feet. And in that understanding, there's wonder, there's humility, and there's hope, because the more we know about this planet, the better we can care for it, not just for ourselves, but for all the life that shares this remarkable, ever-changing world with us.